Welcome, pre-calculators. We are here to do some verifying of identities using the sum and difference formulas. Verifying identities is something that we're asked to do quite a bit in pre-calc or trig, and it's really just to prove that we understand how these things relate to one another and that we're able to use the various formulas and identities that we have. And so I'm going to show you three identities that we might be asked to verify that require use of the sum and difference formulas in order to do so. Okay, so here's our first one, and I'm sorry I wrote that alpha a little bit weirdly small. But first off, what is an identity? An identity is basically a mathematical statement, like an equation, that is true regardless of what values the variables take on. Regardless of what angle I plug in here, it's always going to be true. That makes it an identity, something that is true regardless of the situation. Verifying identities basically means proving that this is true, which pretty much boils down to proving that this side does in fact equal that side. When we are verifying identities, it's not like solving an equation where we start doing things to both sides. We never do anything to both sides, basically, when we're verifying identities. Instead, we start with one side and we work with it and break it down and simplify it or expand it or do whatever we have to do to it to show that we can work with this and do legal things to this and end up with this. Or you could start with this side and show that by manipulating this legally, so to speak, using things that we know to be true, you can end up with this side. Now, very often people do something where they say, this is the left-hand side, this is the right-hand side, and I'm going to start with the left-hand side and I'm going to show that I can get from there to the right-hand side. So let's go ahead and do it that way. Let's go ahead and say the sine of 2 alpha. This is where I'm starting. Well, the sine of 2 alpha means the sine of alpha plus alpha. Remember I said we were going to use sum and difference formulas. So that means we get to use the sum formula for sine. Recall from when we talked about sum and difference formulas, that's the third one there. The sine of a sum of two angles is the sine of that angle, one angle, times the cosine of the other, and then we flip-flop the cosine and sine. So that's exactly what we're going to do. Let me go ahead and write that down for you first. Okay, so here's the sum formula for sine, and in this case, we don't have a different angle for our second angle. It's the same angle. So basically, this is what we're going to write. We're going to say, okay, this equals this. That's the next thing I'm going to write. The sine of alpha times the cosine of alpha plus the cosine of alpha, sorry, that's a weird alpha, times the sine of alpha. Well, these are the same thing. When you multiply, order doesn't matter, right? Commutative property. So this is like saying x times y plus y times x. These are the same, so I could rewrite that as two of them. And voila, that's where I was trying to get. This is my right-hand side. Okay, so that means I'm done. Sometimes people like to, instead of saying left-hand side, right-hand side, put a check mark when you're done. I've heard of people who did a smiley face when you're done, when you've gotten to the point where you can say, hey, look, this is the other side of that identity. I've proven that that does indeed make the same thing as that. They are the same. I used to like to do the double lines. Sometimes people call those a railroad track, or QED, which means basically quod erat demonstratum. It's been demonstrated. That means I'm done. Different ways of saying I'm done. All right, next up. So I promised you that these were going to be identities that use the sum and difference formulas, and this one makes it pretty clear right here on the left that, yeah, that's exactly what we're going to do. So I went ahead and pulled up my sum formula for sine and my difference formula for sine, because I'm going to use each of them to go ahead and start simplifying my left-hand side. So I'm going to start with that. I'm going to say, okay, the sine, and I'm rewriting what I've got, is equal to, and I got all of this mess times all of this mess. So this is going to be a challenge to get on one page. So let's see what we can do here. So sine alpha cosine beta plus cosine alpha sine beta times sine alpha cosine beta minus cosine alpha sine beta. I made it. Okay, so what we have here at its root is something like x plus y times x minus y. I have a binomial, 2 terms, times another binomial, 2 terms, which means we're going to distribute or use FOIL, basically. So these get multiplied, these get multiplied, these get multiplied, these get multiplied. This is another way of drawing sort of the connections that I've heard students call the lobster claw. It's like a big claw. But it really doesn't matter what you use as long as you multiply everything over here with everything over here one time. So sine alpha cosine beta times sine alpha cosine beta. I'm going to go ahead and simplify that and say that's sine alpha times sine alpha, so that's sine squared alpha. Cosine beta times cosine beta is cosine squared beta. All right, that's the first. Then I've got this guy times this. Sine alpha, and this is minus, this is positive, so it's going to be minus. Sine alpha times sine beta times cosine alpha, and I'm just trying to put it in some order that might make sense to me. Then I get to do these two. They're both positive, so that's going to be a plus. Sine alpha times sine beta times cosine alpha times cosine beta. I've got all of those right there. Look what's happened here. And then last times last, cosine alpha times cosine alpha. That's cosine squared alpha. Sine beta times sine beta is sine squared beta. These guys will add to 0, and I will have sine squared alpha cosine squared beta minus cosine squared alpha sine squared beta. All right. Now the problem is, and sometimes this is, by the way, what I just did is a very common thing to do in the process of verifying an identity. You start with one side and you say, hey, I can apply a formula, or I can break that down somehow. So I apply the formula, then I simplify the formula, and then I get somewhere. And then sometimes you go, well, I don't really know what else I can do. So you go back and you look, where am I headed? Where is it I'm supposed to get? Well, notice that I'm not going to have any sines at all in my answer. I'm only going to have cosines. Another thing to notice is that everything's squared here. So what I'm going to do is I'm going to use that old Pythagorean identity that says sine squared plus cosine squared is 1. So if I want to rewrite a sine squared, I could call it 1 minus cosine squared. So I can put that here in place of this, and also over here in place of this. So let's do that. This is 1 minus cosine squared of alpha. And this is 1 minus cosine squared of beta. And now I can distribute for both of these. I have 1 term times 2 terms, so I distribute. So this gives me cosine beta, squared beta, minus cosine squared alpha, cosine squared beta, minus cosine squared alpha, plus, minus times minus, cosine squared alpha, cosine squared beta. Once again, we have 2 that are going to add to 0. Those 2 are exactly the same. They add to 0, and that gets me down to cosine squared beta minus cosine squared alpha, and that's exactly where I was headed all along. I've hit the right-hand side, so I've shown that this is equivalent to this. And I am done. Let me point out, by the way, that very often when we finish problems and we get the answer, we circle the answer. But it wouldn't really be appropriate to circle this necessarily, and I could write, I didn't really keep writing equals, but I can all the way down here. Because the answer for a verifying an identity, the answer is everything from here to here. It's all of it. All of that work is the answer. Rewriting it as this, and then rewriting that as this, and then rewriting that as this, etc. All of that is my answer. So it's not like this part here is an answer. It's more like, look, all my work has shown you that this is the same as this. All right, here we go. Last one we're going to verify. And you notice we have a tan of a difference. Okay, so we're going to use the difference formula for tangent. And if you recall, that one looks a little bit messy. It's the bottom one here. But the beauty here is they've given me an actual angle, and so I'm going to be able to simplify that part of it. So again, I'm going to start with the left-hand side, ignore the right-hand side for now. I don't work with both sides, remember. I just work with one side at a time. Or pretty much just work with one side, period, until I get to the other side. And I'm going to apply this. This is tan pi over 4 minus tan theta all over 1 plus tan pi over 4 times tan theta. Now, what's the tan of pi over 4? Remember that pi over 4 is right in the middle of the first quadrant, where the sine and the cosine are the same number, so when you put one over the other, you get 1. So this is what we have. 1 plus, this is a 1. So that simplifies pretty quickly. Now this is one of those times that I go, now where is it I'm trying to head? Oh, I'm trying to get here. So somehow I'm going to have to get from everything about tan to talking about cosine and sine. So I know that tan is equal to sine over the cosine, and I'm going to rewrite it as sine over cosine, both in the numerator and in the denominator. All right, now in the numerator and in the denominator, I have addition or subtraction with a fraction. In order to add and subtract fractions, I have to have a common denominator. So I'm going to think of this 1 here as cosine over cosine, so that I have that common denominator. So cosine over cosine minus sine over cosine on top. And in the denominator, cosine over cosine, 1, plus sine over cosine. And now I'm going to rewrite this and say I've got two fractions with a common denominator. I can rewrite that as one fraction. Cosine minus sine all over cosine. That's just the numerator, the part I've written so far. Then I can do the same thing to the denominator. Cosine plus sine all over cosine. Now, remember, this was where we're headed. We're pretty much there. If we recall that when you divide fractions with the same denominator, the denominator basically cancels. But let's show that, just to make sure we are showing all the work we need to. To divide fractions, remember, you take the top one, the numerator, divided by the denominator. Okay? The denominator is a fraction. When we divide by a fraction, we multiply by its reciprocal. So that's how I divide those two fractions. That's why the cosines will cancel. And that's why I end up with cosine minus sine on top, cosine plus sine on the bottom, and that is where I needed to go. That's what I was trying to prove, and I have proven it. Ta-da! Thanks for watching. See you next time.